All right.
What else?
What else is there? There's the area, regular area of a trapezoid.
Okay. Trapezoid is a lot like a rectangle. What's the area of a rectangle?
Base times height.
Well, the area of a trapezoid is the same thing, only there's two different bases, right?
Right.
So it's the average base.
So base 1 plus base 2
Divided by 2.
times the height.
Right. In other words, here's the average base. Multiplied by the height. Gives you the area of a trapezoid.
Okay.
This is fairly complicated to remember. People don't like memorizing complicated formulas that have lots of terms in them. So the way I memorize the area of a trapezoid, it's the average base times the height. And I know that somewhere in here there's an average base. I don't know what it is, but I certainly know how to add base 1 to base 2 and divide by 2, which gives me the average base.
Okay. All right. How do you? No, never mind. What about the area of a hexagon, pentagon, things like that?
Let's do the area of a regular polygon, which includes hexagons, pentagons, septagons, nonagons, anything. Let's draw a hexagon, a regular hexagon. It has to be regular for this formula to work. Okay, this is the area of a regular polygon.
Okay.
Is equal to 1/2 the apothem times the perimeter. So let's say they gave you a side length of 6. And that's all they give you.
Okay.
Well, there's the center. If I take and connect my center to the vertices, I end up with 6 triangles like that.
Okay.
The apothem is the line that goes right through the middle of each of those triangles. So let's take this triangle and draw it separately like this so we can do the math on it and solve for the apothem. Well, this base is 6. Do we know this angle?
No.
Yes, we do. There's 6 equal triangles in there, and we know that all of the angles together add to 360.
So you do 360 divided by 6?
That gives you what is called the central angle. In other words, each of these angles here is 360 divided by 6. So they're each 60 degrees. So this broad angle here is 60. Well, I don't really need the broad angle. I need this tiny angle here. What's that tiny angle?
30.
Now I have a 30-60 triangle which I can solve.
That's what else I need to put on my card and my cheat sheet as well, is the way those look.
Well, the key with finding the area of a regular polygon is step 1, find the central angle.
Right, I understand that. What I'm saying is, can you give me, like, with similar triangles, what's on
Sure,
36
sure,
90s?
sure. First of all, what's this dimension here?
Which, 3.
Okay, there's a start. So here's our unit, 3060. We know this is a right angle here, so this is a 3060 right triangle. What's our dimensions on their unit one?
On our unit, that's, remember, it's like 1, 2, all right, yeah.
Okay, so how do I apply this to this model here?
You gotta find the simple, I don't know what it's called, like common factor.
Scale factor. It's called it's actually called a similarity ratio.
So, which would be 1 to 3.
3 to 1.
3 to 1.
Always use the bigger triangle as your top.
Okay.
Because most of the time when you're solving triangles by using similar triangles, you're always solving a triangle that's bigger than the one that you're going to put on your cheat sheet. Okay. This is the unit 3060 triangle.
Right.
By unit, I mean opposite the 30 is always 1. Opposite the smallest angle is always 1. Okay, I could have said 2 roots 3, and 4 just as easily.
Okay.
But I call it the unit for a reason, and that's so that I can put 1 as the opposite of the smallest angle, and that makes the rest of the dimensions that. So what's the similarity ratio?
3 to 1.
So every side in this triangle, what's that hypotenuse equal to?
6 to 1.
What's the apothem equal to?
3 root 3.
Now we're ready to solve for the area. In other words, you find the central angle by dividing 360 by however many sides you have in your regular polygon.
Okay.
You take half of that to find this angle, because we're always going to take that triangle and draw the apothem down the middle. And then you solve that little half triangle for the apothem. And it won't always be 30 degrees. If we had a 7-sided figure, well, that angle is going to be 36 degrees. Oh, that doesn't make any sense. 360 divided by 7 is 52. So that would be 26 degrees. In other words, only the hexagon gives you a nice, convenient 30-degree angle here, whereby you can solve for the apothem using similar triangles.
Okay, but if it gives you something that doesn't leave you with like a 45, 45, 90, or 30, 69 triangle, what do you do?
Use trig. So let's take the same problem, only this time it's a septagon, 7-sided.
Okay.
So the central angle is going to be 360 divided by 7. Well, that goes in there 52 times. So each one of these angles would be 52 degrees.
Cut in half. That's 26.
So that's 26. So now we're dealing with a 26-degree tiny angle. And this is side 3. So we can't use similar triangles because we don't have one with a 26-degree angle in it. So now we have to use trig. So how can I use trig to solve for A?
Opposite, adjacent, so that would be
Good.
TOA.
Tangent.
Tangent, there it is.
Start off with the trig function and the angle.
Alright, tan of 26 equals 3 over A.
Okay, so multiply both sides by A gives us that. And now solving for A would be 3 divided by tan of 26. And there's your answer for the apothem. But let's not get we forgot to do the final step. Once you get the apothem, you're still not in the clear. We got to get a perimeter.
Which is 6 times 6, right?
Right. Okay, so you know how to do that easy enough. Okay.
Yeah. perimeter's easy.
Okay, so the apothem is everything. Just make sure you know this P stands for perimeter, because this can be written a different way. The way I actually prefer it to be written is 1/2 the apothem. Well, P is the number of sides times the side length. We always need to do that. In other words, we're never given the perimeter outright. We're always given a side length, so you always have to multiply the number of sides times the side length to get the perimeter.
Right.
All right.
What else is there? Are there any more like harder area formulas that I need to know? Surface area formulas?
Well, not that I can think of right off my head. I mean, there's lots of them, but I don't know which ones you've had. I'm trying to think of what we've covered that's not a cone or a pyramid. How about a prism? Now, the problem with these is that I can't draw them. I'm no good at drawing a pentagonal prism. If you have a prism, you know what a prism is? Has two equal, parallel, and opposite sides. So a brick is a prism, a cube is a prism, a cylinder is a prism. Because on a cylinder you have two equal and opposite sides that are merely joined together by a thickness. So if you're looking for the area of a prism, it's the area of the base times the height.
All right.
Doesn't matter what kind of prism it is. In other words, it doesn't have to be a cylinder. The cylinder is just a different kind of prism. So for the cylinder, I've got the area of the base times the height. If I make this, instead of a circle, I make it a pentagon, top and bottom, then it would be the area of the pentagon times the height. And the area of the pentagon is that. So,
all right. Let's see.
Let's talk about your review material that they gave you for your test. Have we gone over it all?
No.
Well, let's bring it up and have a look at it and see if there's anything on it that you don't know. Can you paste the link in here?
Okay. Yeah. What is the unit triangle for a 45-45 triangle?
Okay. Well, you can figure that out actually pretty easily, because remember what I said about unit? What does that mean? Means that it's 1 opposite the smallest angle. Well, if this is 1, what's this?
2. No, 1.
If that's 1 and that's 1, what's this?
Would that be root 3?
Use the Pythagorean theorem. The hypotenuse is equal to what?
1 squared, the square root of 1 squared plus 1 squared. Okay.
That's why I said you can figure it out, because once you get the 1, this has to be 1, and then this is easy, square root of 2. So the unit 45-45, you don't need to write that down anywhere. As long as you remember that unit means the side opposite the smallest angle is 1, you're good to go. The 30-60, on the other hand, you do need to memorize that that other side is square root of 3.
All right.
You could figure out the hypotenuse once you knew that, but knowing that that's square root of 3 is not obvious.
Right.
Okay. I'm happy to answer questions for you if you have them. Or we look over your review pamphlet and just see if you have any problems that are going to give you trouble, and we'll talk about them.
I'm pulling it up right now.
All right.
This looks like it is. So,
we'll need something to do tomorrow also. So
it'll be the review packet.
Okay. This review packet?
Yeah.
Okay, now we did something on here, didn't we? We've done a number of things.
24.
24?
24.
Okay.
24.
Okay. So how many problems are on this thing?
Roughly 72, I think.
72. So I guess my question is if we just start from 24 and go down, will we be able to cover them all by tomorrow? And I think the answer is no. So
right.
you need to tell me which ones you want to do and which ones you don't want to do.
Let's do 24, and if I feel like I know it, we'll skip whatever comes up.
What's angle 1?
What do you mean, what's angle 1?
They want to know the measure of each numbered angle.
All right.
What's angle 1?
I don't know.
It's the first step in finding the area.
Right. Sorry, we just did this one. It would be 30.
Not angle 1.
No, angle 1 would be 60, sorry.
Okay. Angle 2?
Angle 2 would be 30.
There you go. What's angle 3?
Angle 3 would be 30 as well.
No. If angle 1 is 60, what kind of triangle is that?
30, 60, 90?
No. It's an equilateral. Doesn't it look like an equilateral?
Yeah.
Okay. It's an equilateral because it's isosceles for sure, because all radiuses are equal. So this radius is equal to this radius, which means this angle is equal to that angle, if you can see my cursor.
Yeah.
And since angle 1 is 60, and these two have to add to 120, they each have to be 60. So it has to be 60, 60, 60, because this is isosceles.
Okay. So angle 3 would be 60.
Yeah. Okay. Now let's take a different situation. Let's say angle 1 is 80. Now what is this angle? What would angle 3 be if this central angle was 80?
Have to be 80 as well because it's an equilateral.
No, but the central angle wouldn't be 80 if it was an equilateral. In other words, I'm not saying for a hexagon. Obviously, for a hexagon, that central angle has to always be 60. But if I had a, well, I guess no shape gives you 80 as a central angle, so let's look at a septagon. Let's take a 7-sided figure. The 7-sided figure is going to have a central angle of what?
You said 52.
Okay, so what is this angle? 2.
Wouldn't it be 52 as well?
No. This is an isosceles triangle. That side's equal to that side because I can draw a circle around this thing. Not a very good one, but I can get you to imagine a circle drawn around that. So what is angle 2 and what is angle 3? They're both the same. What do they have to be?
Oh, because they have to add up to 90, right?
No. All three angles have to add up to what?
180.
Okay, so what's angle 2 and 3 have to be?
Subtract 52 from 180.
Okay.
That's 128. And then divide that by 2. Does that come to 64?
64.
Yeah.
Angle 2 is equal to 64. So that's the way
Okay.
you find these angles, is if you know the central angle, then these angles are always equal to one another. And you can do the
Right.
math no matter what that central angle is.
Right.
Okay. So on this problem, we've got angle 1, 2, and 3. Let's go to the next, 25. Find the area of this regular polygon.
Right.
First of all, what kind of regular polygon is that?
That is an octagon.
Okay. So what is its central angle?
Central angle? 8.
Remember, that's the first step in solving for area. Always. We have to find that central angle in order to be able to calculate the apothem.
Okay, so it would be, wouldn't it just be 8 then?
Central angle is always 360 divided by the number of sides you have.
All right.
Because notice what I can do with this octagon. I can break it up into 8 triangles by just connecting the center with each vertex. And then the central angle is that angle of that triangle, of one triangle.
All right.
So since all the triangles have to add to 360, I'm going to take 360 and divide it by how many triangles there are. So it's always 360 divided by the number of sides you have, which in this case is 8. So that number is 45. So the central angle of an octagon is 45.
Okay.
So in order to solve this problem, we need to find an apothem. So first of all, I'm going to take one of these representative triangles that I would get if I connected the center to each vertex. This is 45. Now I'm going to draw a vertical and solve this triangle for A.
All right, so 45 gets cut in half.
So this is 22 and a half. What's this dimension right there?
5.
Give me a trig function for solving for A.
It'd be tangent again, so the tan of 22.5 equals 5 over A.
And notice that we always end up with that apothem in the denominator, unfortunately, because it makes it a little harder to do.
All right.
In other words, it would be easier if it was A over 5, but it's not. The apothem always is in the denominator. And it's always tangent. In other words, we're always using the tangent function to solve these little triangles.
Right.
Okay, so you can solve this for A, okay?
Yep.
Okay. Once you solve it for A, you can plug it in for that, okay?
Yep.
Okay. Interesting. That they even gave us the 13.07. We don't need it. Notice that had I incorporated it, though, that makes this ignore the central angle. You don't need it in this case because they've given us the hypotenuse of that triangle. So if I have the hypotenuse and I have this edge, which I have from just this information and that information, well, I can figure out the apothem without knowing that angle.
Right.
Because it's a right triangle, and I've got two sides of a right triangle, so I can always solve for A. So they didn't actually need to give us this dimension, 13.07. Notice that we didn't use it at all because we solved it using trig.
All right.
Okay. You comfortable with not figuring out what the precise answer is? You know how to do it.
Yeah, that's fine. It just takes less time to solve problems then.
Yeah, we don't want to spend our time on arithmetic. We want to spend our time on setting these things up. Is your test going to be all multiple choice?
Yeah.
Okay. That does actually matter, but it shouldn't. We're going to pretend like it's not going to be multiple choice, because I don't really ever look at the multiple choice answers here. I just solve the problem and then find that answer from the multiple choice.
Right.
So give the ratio of the perimeters and the ratio of the areas of the first figure to the second figure. Let's start with the similarity ratio. They didn't ask for that, but I'm going to ask for it. SR is equal to what?
40 to 15.
Okay. What's the perimeter ratio equal to? Perimeter is a linear measurement.
Right, but they don't give you all the side lengths.
You don't need it. When I said it's a linear measurement, I said that because it's the same. In other words, the similarity ratio is also a linear ratio. By linear, I mean it's only yards. It's not yards squared. It's not yards cubed. It's just yards. When I figure out the perimeter of this, it's going to be in yards. When I figure out the perimeter of this, it's going to be in yards.
Right.
Well, the perimeter ratio is exactly the same as the linear scale factor, which is called this similarity ratio. So the perimeter is also 40 to 15. What's the area ratio?
Would it be 40 to 15? No. You'd square that then. Wouldn't it be 40 squared over 15 squared?
Very good. If this was a solid, what would the volume ratio be?
40 cubed over 15 cubed.
Okay, that's all you need to know for these kind of problems. And it doesn't matter whether it's a quadrilateral, a trapezoid, a pentagon, a triangle, a circle, anything. When you go from linear to area, you have to square both top and bottom. When you go from linear to volume, you have to cube top and bottom.
Okay. I was going to say skip 27, but it looks like a different problem. Find the area of the larger.
It's not actually a different problem. It's the same kind of problem. In other words, they're giving us the scale factor.
Okay.
What's the scale factor?
45 to 40.
So what's the area factor?
45 squared to 40 squared.
Let's put a number on that.
Let me pull out my calculator here. 45 squared is 2025 over 1600.
What's that number?
What do you mean, what's that number?
What's 2025 divided by 1600?
Oh, sorry. 2025 divided by 1600, 1.26.
Okay. So we've just calculated the area ratio. Right?
All right.
In other words, we were given the linear, 45 to 40. From this, we know what the area ratio has to be. Has to be 1.26 to 1.
All right.
Now they're telling us that the larger triangle is 2015. So 2015 compared to the area of the smaller triangle, which we're trying to solve for, has to be the same as 1.26 to 1.
So can you divide 2015 by 1.26?
That's the answer.
Okay.
But setting it up is really the trick. It wasn't solving for it, it was setting it up.
Right.
Okay. Find the similarity, number 28, the similarity ratio and the ratio of perimeters, knowing immediately that those are the same. In other words, the similarity ratio is always the same as the ratio of the perimeters.
Right.
Okay, so all we really need to do is find the similarity ratio of two regular octagons, one of which has an area of 18 and this one has an area of 50. So what's the area ratio of the big to the little?
Well, it says 18 squared, so would you square it?
No, it's not. It doesn't say 18 squared. It says square inches. That 2 does not apply to that 18.
Okay, so the area ratio is 18 squared over 50 squared.
No, the area ratio is 50 to 18. Bigger number on top always.
Right, sorry.
Okay, and there's nothing squared about it. That's just the area ratio.
Okay.
What do I know? If I know the area ratio is that, what does the similarity ratio got to be?
The square root of 50 over 18?
Square root of 50 over the square root of 18.
Right, sorry.
Okay, so that's the answer. Let's see. In this case, they actually do the smaller to the larger, which is fine. It's the square root of 18 to the square root of 50. So I'm looking for that. Well, let's see. What is that? That is 18 is, my cursor disappeared. Square root of 18 is 3 square roots of 2. The square root of 50 is 5 square roots of 2. There's your similarity ratio.
All right.
Notice that answer A is correct because the similarity is the same as the perimeter ratio. Perimeter is a linear measurement. Whenever you're comparing linear measurements, the ratios are always the same. It's only when you go to areas that it's the square of the similarity ratio.
Okay.
So when they give you the areas, you have to take the square root to find the similarity ratio.
All right.
Okay, let's look at 29. What do they want on 29? The area, well, find the circumference.
That's easy. Circumference is pi r squared, isn't it?
No.
Oh, that's area. Circumference is 2 pi r.
Okay. So, you know how to do this one? Shall we go on?
Yeah.
Okay. Notice that when you're talking about circles, they can give you any one thing, and you have the ability to calculate everything else. In other words, if they give you the area, you can figure out the radius, and with the radius, you can calculate anything you want. If they give you the circumference, you can calculate the radius. If they give you the radius, you can calculate the radius. If they give you the diameter, you can calculate the radius. So let's start with finding the radius. If the circumference is equal to 60 pi, what's the circumference equal to?
Pi r squared.
2 pi r.
I'm sorry.
Okay, so what's r?
R, the circumference is 60. 30 then?
Okay, they want the diameter. What's the diameter?
Diameter would be 60 as well.
Okay, and they want the length of an arc of 140 degrees. So here's our circle with radius 30. And they want the arc. This is a 140 degree angle, so this is a 140 degree arc. So from there to there is what?
There to where?
From A to B. What's the measurement of that? They want the length of that arc.
Would it be 110?
No.
Well,
Where'd you get 110 from?
110 plus 30 would give you 140, but...
No, 30 is the radius. That's not an angle.
Right, it was a shot in the dark there. Would it be 60 as well, because they're both radiuses?
Okay. When you are asked about arc length, like this, the only thing you know how to do is figure out the circumference of that circle. We have that, in fact. The circumference was given to us. It's 60 pi.
Right.
What part of the circumference is that arc?
That arc covers 140 out of 360.
Okay. So it's 140 divided by 360. That's the percentage or the part of the circumference that we're dealing with.
All right.
That's the answer, whatever that number is.
Okay.
In other words, all of these are the same. When they ask you about a particular arc, you are concerned with the whole circumference and what percentage of the circumference that arc is.
Okay.
If they ask you about the area of a sector, you care about the area of the whole circle and what percentage of the full area of the circle is that arc. So those are the two questions that could give you trouble, is finding an arc length and finding a sector area. Just remember that whenever they ask those, you have to find the area of the circle or the circumference of the circle for starters.
Okay.
And it's whatever that angle is divided by 360.
All right.
So here's an area of a sector problem, 31.
All right.
So start out with the area of the full circle.
2 pi r.
No.
Oh, the area of the circle. I saw sir and I thought circumference.
Well, here's the difference. This is an area problem. This was a circumference problem. So when we were trying to find the length of that arc, we cared only about circumference. When we're trying to find the area of this sector, we care about the area of the full circle.
Right. I got that mixed up in my head because you wrote a cert.
Okay. Oh, circumference. Yeah, right. Okay. So it's pi r squared. So in this case, it's what?
2 pi.
Pi r squared.
Right. So it'd be the radius of 9 squared. Okay, 81 pi.
So that's the area of the whole circle. What part of the whole circle is this?
Only 135 over 360.
So that's my multiplier.
Multiplier? Don't you mean you divide that?
No, I multiply this by the area of the full circle. because I'm only dealing with this part of the circle. I'm dealing with about a third of it.
Okay.
So it doesn't matter whether it's area or circumference or length of an arc. We have to find the ratio of the full circle, and we always do that by taking this angle and dividing it by 360. That gives us that this is about a third of a circle. When I say about, if it was 120 divided by 360, that would be exactly a third. 135 divided by 360 is a little bit more than a third. But that's the way you want to look at these problems. These problems are always, well, what percentage of the full circle is that? What percentage of the full circle is that arc of 140?
Okay.
Okay? All right, let's go for another 5 minutes here. Let me see if I can draw this one. Maybe you don't need me to draw it. The radius of the bullseye, that small circle, is 8. The radius of each concentric circle is 8 inches more than the radius of the circle inside it. So I think we do need to draw it. Give me that measurement.
It's half of the
First sentence. First sentence.
It's 8.
Now give me this measurement.
16.
Now give me this measurement.
24.
And finally, this radius.
32.
Okay. If a dart lands at random on the dartboard, what is the probability that the dart will hit in area C? Wow.
24 out of 32.
Okay, area C on my diagram is this.
Right, which is 24.
No, 24 is the radius of that full circle. How do I figure it? Let's do this one thing at a time. What's the area of that shaded region?
Pi r squared. But
No, conceptually, shaded region problems are subtraction problems. So when I ask you the area of a shaded region, we're going to take the area of the outside circle, not the outside circle in my picture, but the circle outside the shaded region, minus the area of the circle inside the white. In other words, the area of the shaded region is always the area of the outside minus the area of the white inside. So what's the area of the outside circle there?
I don't know because it doesn't tell you that.
We got the radius. If you know the radius of these circles, you know everything there is to know about them.
Oh, so it's 32 squared.
It's not 32, though.
Of the outside of it?
Well, I didn't mean circle D. They are asking about the area of C, this area right here.
Okay.
So when I take the area of the outside, I want the area of this circle right here. What is that?
Okay, so 24 squared.
Okay, so 24 squared pi minus the area of this inside circle. What's the area of that?
16 squared pi.
There's the area of the shaded region.
Okay.
Now, first of all, make sure you understand why that's the case and why I didn't have to even care about this middle circle.
I understand that because that's not what's...
So what I'm doing here, to find the area of the shaded region, I took the area of this circle and subtracted the area of this circle.
Right.
That's what I mean by shaded regions are always subtraction problems. I don't care about the inside circle because it's white. I only care about this in middle circle here. So it's 24 squared pi minus 16 squared pi. Now, when I'm talking probabilities, what's the probability that a dart will land in this shaded region? What is the probability of something landing in a particular area?
Well, then you do the area of all the sides minus that.
No, we take the area of the shaded region.
Right.
And divide it by what?
Divide it by 4.
Divide it by the whole area. In other words, if I'm throwing darts, that dart could hit the bullseye, it could hit here, could hit here, could hit here, could hit there, could hit in there. So when I'm figuring probabilities based on areas, I want the area of the shaded region divided by the area of the whole dartboard.
Okay.
What's the area of the whole dartboard?
Then you do it bit by bit, wouldn't you? Like.
No, the area of the outside circle is the area of the whole dartboard.
Oh, so 32 squared pi?
There's your answer.
Okay.
Whatever that comes to be.
Okay.
Okay? All right, so we got through 32. We'll see how many of these we can knock out tomorrow.
Okay.
I will talk to you at 5 o'clock tomorrow.
All right, sounds good. Thank you.
Okay? All right, Ryan. Bye-bye.